Good day, ladies and gentlemen, personalities. We are going to speak about calculus, but in calculus we are going to speak specifically about the second derivatives and things that comes out of a second derivative. So you are talking about things like minima and maxima, and then you are also speaking about the issue of concavity, and then you are also speaking about the point of inflection. So at the end of this session, you should know, number one, what is a minimum and what is a maxima, and then what is concavity, and then also how do you see concavity, and then also how to find the point of inflection, and then how to answer all questions that surrounds these 3 point minima versus maxima, concavity, and point of inflection. So that is what you should know at the end of this session. This is for grade 12. That is paper 1 for calculus, for CAP syllabus in South Africa. And then so basically the things that we're going to be speaking about here are going to come out of your test, and they are going to come out of your exam as well. So make sure that you go through them carefully. And by the way, before we even continue, if you want to become a part of this community Tembela Maths Club, you can go ahead and click the subscribe button below. And then if you do want to be notified if there is such communications, then if I upload a video around these things or something else in mathematics, then you can also click a notification button. So let's get straight to the chase. So we are going to start with concavity. So when you are speaking about the concavity, there are 2 pathways in which concavity can take. So the first part of concavity, let's say concavity, there is concave up. So when a function is concave up, it's when a function is like this, okay? And then we refer to it as CCU, which means concave up, okay? So we'll be using this CCU for concave up, okay? And then the second part is concave down. So when the function is concave down is when the function is standing like this. So concave up is like a cup that is facing up, and then concave down is like a cup that is facing down like this. And then we usually deplete it with CCD, which means concave up and then concave down. And then at this level at grade 12, you are usually facing with a situation where you've got something like this. You've got a graph that you are dealing with, and then this graph has something like this. Say you've got, there we go. Anyway, let me use a different color. Let me just write this Y here, and then X here, and then let me use a different color here. Okay, there we go. There we go. Okay. So you've got a graph here, and then as you can see, along this point, the graph is concave up. So it's facing up. Can you see that? And then at some point, it starts facing what? It starts facing down. Can you see that? So this is concave down. All right. So now what we are going to do is we are going to zoom in into a point. So I'm going to give you a point, and then this point we'll call it C. So say a value of x, which is x, is equal to C. And then what we are going to ask is whether at this point the function is concave up or concave down. So what is it that you should do on your side when we ask you this kind of question? You should actually look at this function C. So if this function C is here, without thinking, you can see that things are concave up here. Okay, so and then you will then tell us that, okay, at this point C, the function f at x, because this is function f at x, let me just quickly write it, y is equal to f at x. Okay, so if this function is here, you know that at this function the graph is concave up. And if this function is here, you know it's concave up. If this C is here, because C we do not know what it is, but if the C is here, you can see that the C is at the part of a graph that is concave down. So those are the things that you're going to be looking at. When I give you C, at that point, is it concave up or is it concave down, right? Now, the question is, how do you get to see that? Okay, so in order to decide about whether at a point the graph is concave up or concave down, what you will simply have to do is nothing other than find a derivative of the particular function that you are kind of facing. So for example, here you must find f. You already have f. You must find f prime at x. Okay, you must find f prime at x. Okay, so f prime at x will be whatever that you find. We do not know, and we also do not care. But now, after finding f prime at x, you should then take this value that you are interested in to find whether the graph is concave up or concave down at, right? And then keep it on a standby, right? So, okay, you had a graph, and then you have the function, right? Now, after you've found this function, you must then find a second derivative. That is f prime prime. So you must take whatever value that you find here, and then you must find the derivative of that function. So you get f prime prime at x, whatever it is. Now you must take this value c, and then you must substitute it into this f prime prime, right? Now I want you to hold your seat because we are actually about to move further. So if f, okay, let me actually use a different kind of a color so that we can see this. If f prime prime at c, if you get a number that is greater than 0, that means, what does that mean? That means that you've got concave up. Can you see that? And then if f prime prime at c is less than 0, so what do we have? You have concave down. Okay, does that make sense? Now if we put things well into perspective, let's put things nicely just to summarize everything. But before we even summarize anything, what about f prime prime? If f prime prime is 0, so what do we say about concavity at that point? So if f prime prime, if we have f prime prime at c, which is equal to 0, therefore it's neither of the two. So it is not concave up, it is not concave down. Okay, so there are three cases. It's either something is concave up, or something is concave down, or something is not concave down and is also not concave down. They will be down at this particular point where f prime prime at c is equal to 0. Then at that point things are not concave up, another concave down. So let's just put this thing into perspective. So how do we do that? Okay, we say when we talk about concavity, what we do, we look at f prime prime at x, right? So f prime prime at x, but this x, you take this point that you are looking for, which is c in this particular case. So if f prime prime at c is greater than 0, what happens? That tells you that you've got concave up. So a concave up, it's something that is standing like this. Let's say it's something that is standing like this. And then, but if, okay, let me actually use a different color so that I can put a distinction between these two. So if f prime prime at c is less than 0, so that means you have what? You have concave down. Now when you have concave down, then you have something that is standing like this. Okay, so Mr. Maxaba, what are you saying to us? I'm saying something simple, that if you've got f prime prime at C, therefore if you have f prime prime at C which is greater than 0, then at point C you've got concave up, and then if f prime prime at C is less than 0, then you've got concave down, which is something that looks like this. And then lastly, with a very different color again, if f prime prime at C is equal to 0 this time round, so what does it mean? Not concave up, and then also not concave down. Okay, so right now if I can give you any point and ask you as to whether is the graph at this point concave up or concave down, then you will know exactly what to do, because you will just take that function, find the derivative, find the second derivative, and then substitute that function not anywhere else but on the second derivative. All right. All right, so let us take an example so that we can see how we deal with these issues of concavity. So in this example, you will do the following. Let's say they give you the function. Let f at x be equal to, say, x to the power 3 plus 2x squared plus 4x minus, say, minus 2. Okay, and then they say to you, is x is equal to, say, minus 1 concave up or concave down, right? You must choose between the two. So as we explained earlier, okay, so as you already have this information, you know what to do here. So what you're going to do, you're going to find the derivative of this. So f prime at x is what? Is equal to 3x squared, right? Plus 4x plus 4. Can you see that? Okay, but you know, because you are looking for concavity, you must find the second derivative. Okay, so f prime prime at x, then you find the derivative of this thing. So this to multiply to this one, you get 6x, and then plus 4. Can you see that? Now this is a second derivative. Okay, now which value are you testing? You are testing x is equal to minus 1. So you'll then say f prime prime at minus 1. And then that is nothing other than 6 times minus 1 plus 4. 6 times minus 1 is minus 6. Minus 6 plus 4 is what? Is nothing other than minus 2. So minus 2, you know, that is a value that is less than 0. Okay, so it's less than 0. So because it's less than 0, what does our theory say? When you have less than 0, you've got concave down. So what is your answer? Therefore, x is equal to minus 2 at x is equal to minus 2. Actually, my question was terrible. I was supposed to say, is f at x cc, or is f at x ccu or ccd at x is equal to 1. So that is a question that I should have. Let f at x be f at x is equal to x cubed plus 2x squared minus 4x plus 2. Is f at x concave up or concave down at x is equal to minus 1? Therefore, here you then find out that x is equal to minus 1, not minus 2, I'm talking nonsense, at minus 1, f at x is what? Is concave. What? Concave. We said concave down. Okay, so we got this one on. Why? Because the derivative at this point is what? It is less than 0. Right. Now let's take the same function and now let's ask a question properly now. Is f at x concave up or concave down at x is equal to, let's take now x is equal to, let's say 3. Okay, you know you have to find the first derivative and then you need to find the second derivative, but obviously we already know what it is. Oh, we can actually pick another okay, let's not pick another number. Let's continue with this one. If, let's say, if f at x is equal to x to the power 3 plus 2x squared plus 4x minus 2. And then again, I'm just going to reiterate this thing back so that you can actually hold it on a line. Alright, so basically, you know, you get the derivative of this, and then which is f prime at x is equal to this times this. It's going to be 3, and then x, 3 minus 1 is 2, plus 4x plus 4, we've already found it here, and then f prime at x is the derivative of the above, and then you get what? You get 6x plus 4, and then now f prime at this value, x is equal to 3, is nothing other than 6 times 3 plus 4, which is what? Which is 6 times 3 is 18, 18 plus 4, what is it? It's 22, and then 22 is what? Is positive. And in terms of our rule, we said if f prime at c is greater than 0, what do we have? We've got concave up. So because of that, therefore, so you can say CCU, and then you then say therefore at x is equal to 3, f at x is what? Is you must write nicely, don't write like me, you must write nicely, concave up. Alright, so that is how you run around with the issues of concavity. Right. Alright, now we are done with concavity. Alright, so now let's look at minima and maxima. Minimum, it's the singular, but if it's many, it's minima. Alright, so it's minima and maxima, which is a plural for maximum. Alright, now, ladies and gentlemen, personalities, when it comes to minimum and a maximum, the story is a very simple one. The minimum and the maximum, you will be given, so what will you will be given there? You will be given one of the turning point or both of them, and then they will ask you whether which one is the minimum and which one is a maximum. So now the question is, if you are given a turning point, whatever turning point it is, how can you tell whether that turning point is minima and maximum? Okay, so basically you let x, which is equal to c, be an x of, it's only the turning point, guys, that it can be minimum or maximum. Okay, and then so you let the x be is equal to c be an x of a turning point or stationary point. They usually use stationary point. So stationary point is just turning point. Okay, don't be confused around it. Okay, stationary point. Now, here's a question that you should be aware of. Now, is x equal to c minimum or maximum? Okay, that is a question that you are dealing with. Now, the question is, how do you go around dealing with this kind of a point? So, what you simply do is, obviously you will have the f at x. You just simply have to find the derivative. If you don't have it already, find it. F prime at x, right? Sorry, f prime at x. Now, when you have found f prime at x, then find the second derivative. So the second derivative, which is f prime at x. Now, you must take this value of c that you've been given. Now, when you have taken this value of c, you must then take this value of c and go back to the concept that you spoke about earlier, concavity, and look at whether at that point is f at x concave up or concave down. Okay, so if you take f prime at c, and then it turns out that it is a number that is greater than 0, then that would simply mean that you've got what? You've got concave up. We saw it from the previous example. Now, when you have a function that is concave up, so what will happen is that you will have at that function, the graph will be like this. Now, remember what we said earlier. We said that this value is a turning point that we are talking about here, and we want to know whether it's maximum or minimum. And the other thing I should mention, this is not just maximum, it's actually local maximum or local minimum, not the absolute one, but we'll talk about that at some other time. So if they say local, so they can either say minimum or they can say local minimum. It's one and the same thing in this context, lovely people. In different contexts, those two things can mean totally separate different things. All right. Okay. So if you have concave up, therefore obviously the turning point that they're talking about here, there's only one turning point. Can you see that? The turning point is here. Can you see it? It is here. So because this turning point, it is here, you can see without thinking that this is a minimum. Then you have what? You have minimum. Okay? But on the other side, if you can take f prime at x and then substitute the value of c, and you have f prime at c being the value that is less than 0. Therefore, you will know what? What is it that you will know? You will know that you've got concave down. Okay? So if you want to know about maximum and maxima, start your gauge vias at concavity. So you've got concave down. So if you have concave down, we all know, we spoke about it, that it's a cup that is facing down. And then as we said that whatever value you're testing is a turning point, there is only one turning point in this particular instance. And what is a turning point? It's a turning point that is here. And you can see without thinking that this is what? This is a minimum, a maximum. A maximum. So if they give you any turning point, and then they ask you whether it is a minimum, and if you want to find out whether the turning point is a minimum or maximum, just take the second derivative and substitute that point and see whether you get a concave up or concave down. If it's concave up, then you know the turning point is the minimum. If it's concave down, then you know that that is what? It's a maximum, right? And then later we'll do an example so that you can be able to see that. But let's just look at one last thing. And what is that thing? That is the issue of the point of inflection. Point of inflection. Okay, now when we speak about the point of inflection, there is something that I want you to notice. Okay, that's, for example, here things are concave up. Here, can you see? Concave up, concave up, concave up, concave up, concave up. And then there's a certain point here when things change from being concave up to what? To concave down. Now, at that particular point, this is it, where concavity changes. Then we call that point of inflection. So what is a point of inflection? A point of inflection is a point where the concavity of the graph changes. Now, guys, I want you to be aware. Sometimes they can just say find a point of inflection, and you all know that when we are talking about point, a point has two parts. There is an x part and there is a y part. But sometimes they can just say find the x of the point of inflection. So either way, however they ask it, how do you then go about finding the point of inflection? So in a point of inflection, we say it's a point where concavity changes. Okay, now how do you find point of inflection? So you find it like this. You take the second derivative again. Take f prime at x, and then you equate it to 0. Right? Now, when you take the f prime at x and equate to 0, you will then find what? You will then find, obviously you can see here, you will solve for x, and then you will find the x of the point of inflection. Okay, now when you have found the x of the point of inflection, you need the y value of it. If they said just find the point, then you need to take the x, then you substitute it on the main equation, not on this equation. So to get y part of point of inflection, you substitute x of the point of inflection into f at x. Remember, a point of inflection is a point on the graph. So that is why if you find the x part of it, you must take it and substitute it in the main equation and then get the y value that corresponds with it. Okay, so from all of these things, we can see very, very simple thing that the second derivative helps us in two ways. It tells us about concavity, whether something is concave up or concave down. When we are given a point, and then we are supposed to test whether f at x is concave up or concave down at that particular point, we use the second derivative. So that is the first job of the second derivative. And then the second job of a second derivative is to get, if we are given one of the turning point, it is only, okay, you can see it graphically, but one of other ways to see whether the point is maximum or minimum is to take a second derivative and substitute that point in a second derivative, and you will get something that is greater than 0. Then you know that you've got concave up, so because of that, then that is what? That is a minimum. And then if you get something less than 0, if you get something greater than 0, it's concave up, and then it's minimum. And then if you get something that is less than 0, then you've got concave down. Then you've got what? You've got the maximum. And then lastly, the job of the second derivative is to help us to find the point of inflection. So in this particular case, you do nothing but simply take the second derivative literally as it is and equate it to what? Equate it to 0. And then solve for x and find the x of the point of inflection. And then when we have found the x of the point of inflection, then you can take that point and substitute it in the y. That is the main equation of f at x. And then you can find the y of the point of inflection. All right. Now, ladies and gentlemen, personalities, let us then take an example that will actually summarize everything that we've just done. And then after that, we can then go ahead and close shops. All right. So basically, at the end of everything, guys, we have to answer questions surrounding minima and maxima. And then, as I said earlier, they can come in any format. You just have to read the question properly and be able to contextualize the answer that you are going to give in terms of what they are looking for. Okay, so in this case, you are given a graph. They say, consider the graph which is f at x is equal to x to the power 3 plus 3x squared minus 9x minus 2. And then they've written the graph for us. We are lucky. In most cases, you'll have to write it yourself. Okay, and then they are saying, find the minimum and the maximum. Okay, and we know, guys, we spoke about it earlier, that the minima and maximum must be what? Must be turning points. Okay, so the first thing that we'll have to do here is nothing other than finding a turning point. So how do we go about and do that? That is very, very simple. We all know how to do that. So you will just say, okay, number one, so you'll just say f at x is nothing other than x to the power 3. Oh, another thing, guys, that you must be careful of. Sometimes whenever you copy a formula so that you can answer it, be very careful, because sometimes you can copy it wrong and then everything goes demakar. All to find that you did nothing wrong. It's just that, and then you start losing marks there and there. So please don't do that. You must always be careful that you've copied it right. I made that mistake as well when I was still a student. So plus 3x squared minus 9x minus 27. Okay, so what you then do, you take, to find stationary point, you then get, let's just say 4, or you get f. Okay, you get the derivative f prime at x, which is equal to, and then this becomes what? It is 3x squared, right? And then plus 6x minus 9. Okay, this is the second derivative. And then for stationary point, stationary, or for turning point, I'm just trying to be fancy. Then you let f prime at x to be equal to what? To be equal to 0. Okay, now in this particular case, you will have what? 3x squared plus 6x minus 9 equal to 0. You can see there's a common factor here, which is 3. You divide by 3 all over. So you divide by 3, and 3 cancels 3, and then you remain with x squared, and then here you remain with plus, okay, 6 divided by 3, that is 2x. Okay, and then minus 3 divided by 9 divided by 3, and then you get what? You get 3, which is equal to 0. And then, guys, when you are here, it's totally up to you. If you want to use what do they call this thing, a quadratic formula to find this, by all means you can go and use it. Okay, now I'm not gonna use it for my own reason. I'm just gonna factorize. It's totally up to you, guys. And then this is x, this is x, and then I have what here? So it's 3, so I've got 3 here, and then I've got 1 here. Okay, now I've got a negative sign. A negative sign is made by what? By positive and negative. So, but now where should I put negative? Should I put negative here and positive here, or positive here, negative here? Okay, we have to find that one out, you must look at the middle sign. The middle sign is plus, so the positive must be in a bigger number, so plus 3 and then minus. Okay, but before I even go further, ladies and gentlemen, please do not forget that you need to multiply this thing out and make sure that it gives you this before you go further. Right, so if I say x times x, I get x squared, and then x times 3 is going to be 3x, and then x minus 1 is minus x. So 3x minus x, what is it going to give me? It's going to give me 2x. So it does give me this, and then obviously minus 3 times 1, I get what? I get this one. So try this one using a FOIL method. Okay, I just use my eyes quickly because I'm used to it. Okay, and because I'm a boss as well. I'm joking. Anyway, so what do you get? X minus 1 and x plus 3 is equal to 0. And then from here, you can see that x is equal to 1, or x is equal to minus 3. Can you see that? So that means that this point here, we've got negative and a positive one, so this one should be somewhere here. Okay, so this is 1. So if we can take this thing to the side, this is 1, and then what about this one? This is minus 3. It's minus, the point there is minus 3. And now the question is, which one is minimum and which one is maximum? Okay, when you look at things, you can see that this one is a local maximum and this one is a local minimum. But at the same time, you still need a proof to show that, and how to show, how do you prove that? You prove that by taking what? By taking the second derivative. So you already have a first derivative, and then you will say f prime prime at x, and then you will then get what? You will then get this times this, you get 6x plus 6. Now guys, let's test this one. Remember, you want the minimum and the maximum, so you already see, but you just want to make sure that you know what it is. But also you want something, because if I give 3 marks for this, I need to see those steps. So these are the steps. So f prime prime at x is 6x plus 6, and then if I test this value, f prime prime at 1 is going to be giving me 6 times 1 plus 6. So it's 6 plus 6, which is, so this is what? This is 12, which is greater than 0. 12 is positive, so because it's positive, then it's concave up like this. So because of that, then this one is a minimum. Can you see? It really agrees with this graph. This is a minimum. Therefore, x is equal to 1 is a minimum. Okay, but guys, okay, here it wasn't simple. Sometimes they can say find the x of the minimum point, but sometimes they will say just find the minimum point. Okay, so now you've got x, which is the minimum point, but if they just say find the minimum point, that means they want x and what? And y. So how do you find y of this? You take this and you put it exactly here. Okay, because I'm lazy, I'm not gonna write it down, but you must write it down when you need to do it. So okay, let me actually do it for this one. So for y of minimum point, you just take whatever value that you've got and then you substitute it in the main equation. We will take f at 1, which is 1 cubed plus 3 1 squared minus 9 1 and minus 27. Okay, so when you put it in a calculator, what to get? 1 is, okay, so you get minus 30, you get minus 32. Okay, minus 32. So the point, actually let's write it with a different color. So the point x is 1, and then y is minus 32 is what? Is a minimum. Please recall that minimum, they simply mean a local minimum. In some questions, they'll be very specific and they say find the local minimum. It's just the same thing. Okay. And then now, okay, so you've found the minimum. What about the maximum? You already know that this one is the maximum, but still you need to show something that you know your story. So how do you show that you know your story? You will take this point. The point is, okay, you already have f prime prime at x, and then what is it? You don't have to find it if you found it. Okay, on the first instance, f prime prime at x is equal to 6x plus 6, and then f prime prime at what is this value? Oh, it's minus 3. At minus 3 is 6 minus 3 plus 6, and then this will give you minus 18 plus 6. Now minus 18 plus 6, what we get? Minus 12, and then that is less than 0. And then in terms of concavity, this is concave. I'm talking nonsense. This is concave. This is concave down. So whatever that is here is what? So whatever that is here is maximum. Okay, so it's maximum. Okay, so the maximum point is x is equal to minus 3, and then also you take this minus 3 and you put it in the main equation, and then when you put that in the main equation, what do you get? F at minus 3. You can put it there, you will see you end up getting 0. So therefore, at the end of the day, you've got x, which is minus 3, and then y, which is 0, being what? A maximum point, or local maximum point. Okay, now I'm very sure, I am very sure that now if you can get questions that are like this, you will definitely know how to play things out. And actually you can see at minus 3, where's minus 3? Minus 3 is it? Can you see? It's the maximum. The maximum is the hill, and then the minimum is what? It's a hill. Can you see it on top? And then the minimum what? So it is in the peak of a hill, and then the minimum is in the peak of what? Not in a peak, in a throw. I don't know if I can call it a peak. It's in a throw, in a valley, at the bottom of the bottom of the bottom. That is where the minimum is. Okay. Now, point number 2, they say we must find point of inflection. We know that to find point of inflection, what do we need? For point of inflection, we need to find the second derivative. But we've already found the second derivative. Where is it? There it is. So we just say f prime prime at. So you let f prime prime at x be equal to 0. So for the point of inflection, you will then say f prime prime at x, which is this, and then you say you've got 6x plus 6, and then obviously when you let it 0, you say 6x plus 6 is equal to 0, and then 6x will give you, take this 6 to the side, it's minus 6, divide by 6 both sides, and then you get x is equal to minus 6 divided by 6 is minus 1. So the point of inflection is minus 1. So they are actually telling you that somewhere here, that is where what? That is where the inflection changes. That is where the concavity changes. Because remember, we spoke about it earlier, and then we said the point of inflection is a point where concavity changes from being concave up to concave down, or from being concave down to concave up. Okay, but now they say a point of inflection. A point has 2 parts. They didn't say find the x of the point of inflection, though they could do that, but they say find the point. So when you have found this one, you still need what? You still need the y of the point of inflection. So the y of the point of inflection is nothing other than f at. You just take this thing and then you substitute it as we said earlier, and then f at minus 1, which is equal to minus 1 all to the power 3 plus 3 minus 1 squared minus 9 minus 1, and then minus 27. And then you can then go ahead and put this in a calculator, and then you will see what you will find. Minus 16. You can test it. Minus 16. So minus 16 is the y of the point of inflection. So therefore, point of inflection is nothing other than what? Is other than x, which is what? Which is minus 1, and then the y, which is minus 16. Now, does this point of inflection that we have correspond to what we have on the graph? So minus 16 will be something below. It will not be. It will be over 27 here. Can you see? But in terms of x, it will be somewhere here in the negative. So it's somewhere here. So the value that we got here shows us that indeed this point of inflection is fine. Because for example, if our point of inflection had a positive number, there was no way you can have a positive number if the point of inflection changes here, since we know the definition of point of inflection, that the point of inflection is where the graph changes. What is where the graph changes? Is concavity. Okay, so we have got things in the right place. Okay, and then the last value, for which value of values of x is f at x concave down? That is the last question that we are going to bring. Now I want you to look at this and look at it very, very carefully. I want the value of x for which the graph is concave down, and then we can all see that the graph is concave down here along these points. Okay, and then somewhere here there is a point of inflection. The point of inflection is here. Can you see? Now the values of x where f at x is concave down is the values of x from here all to this side, because you can see from here it's concave up. Can you see? So it's from here. Now you only find that if you did not have a point of inflection, then you will have to find it, but you already have it, and then you already have the x of the point of inflection. So what the only thing that you need to do now is to answer. And then so how do you go about an answer? You will then tell them that no, the point of inflection is values from that are less than what? Are less than minus 1. You just saw it in the graph. Okay, you just saw it in the graph. And then so for which values of x is f at x concave down, you tell it for x that is what? That is less than minus 1, and then you are done. So ladies and gentlemen, personalities, that is the issue about the second derivative. Let us summarize everything just to show that we've understood and we've met the objective of what we wanted to do today. We're speaking about the second derivative. So now we know what is concavity, we know what is a point of inflection, we know what is a minima and maximum, and then we also know how we are able to find it. And then we have answered a typical question that comes during the exam that talks about this kind of thing. So we are sort of sorted. So ladies and gentlemen, personalities, this is Mqondisi Maxaba from Tembela Maths Club, a club that helps learners to understand mathematics. Thank you very much for tuning in. If you enjoyed this video and you know someone who can benefit from it, please do not hesitate to share this video on any platform. There's a button over there, down there, where you can actually share it. Thank you very much and have a lovely day and goodbye.